In this talk, I'm going to talk to you about my paper on the problem of p to the minus first in locality-sensitive hashing. My name is Thomas Dybdahl Ehle, and I'm affiliated with the IT University of Copenhagen, the Basic Algorithms Research Institute in Copenhagen, and with Facebook. Locality-sensitive hashing is an algorithm for nearest neighbor search. You can think of this data here that I'm drawing as any kind of high-dimensional vectors that come out of your machine learning program, or maybe it's images. You want to pre-process all of this data such that given a query, something like this, you can efficiently identify the nearest point. So in this case, the nearest point would probably be this one over here. We would like the even more general version where you have some radius like this of some distance r, and you just want to return all the points inside of this. This problem turns out to be really hard to solve in general. So what we can do instead is to put a second radius like this. And we'll say this one has radius cr. We tell the algorithm that it's allowed to return something from this radius here. It doesn't have to, whereas the stuff inside the first radius, it has to return that. The stuff outside this radius, it's not allowed to return. So this gives some slack that allows us to come up with more efficient algorithms. The algorithm we come up with is this thing we call locality-sensitive hashing. You can think of it as a way of partitioning the space. And inside this space, we have all our points from before. These points have now all been assigned to a certain partition. So when we come with our query, we also hash that one, and it says, okay, you land in this region here. And now we only have to compare or measure the distance to these 3 points rather than all of the points. Now you might say, but you only have 3 regions here. So what if there's like way more data? Then you've only saved a factor of 3. And another question you might come with is to say, well, but what if your radius is like this? So now we should really return this point over here as well, and that's not in the same region. Okay, so in general, we have these 2 concerns when we analyze locality-sensitive hashing. The first one, there shouldn't be too much data in each region. And the second one, all the close points should be in the same region. We usually want to draw a certain picture. We want to draw this graph here, which has, on this axis here, we have the distance. And on this axis here, we have the collision probability. And for many simple hash functions, that's going to look something like this, where we have here, we have 0 probability, and here we have probability 1. And here we have distance 0, and here we have distance, I don't know, infinity. But then the important thing is the probability here at distance r. Remember, that was the center or the radius of the first circle, where we have some probability and we have some other probability here. Let's call it P2 out of distance CR. And this gap here, of course, we would like this gap to be as big as possible. That's going to mean that this hash function is really good at distinguishing over this distance. In many cases, the initial hash function we have is not very good. Maybe it has this sort of a linear approach. And that's, for example, going to be the case with the common hash function you use for Hamming distance or Jaccard. So then what we do is we try to amplify it. And the way you amplify a hash function is you started out by having this hash function that went from some universe to some range. Now you instead create a hash function, let's call it dash, that goes from the universe to the squared range. And that's simply done by saying that the value at x is some vector where you have you make independent copies, h1 and h2 of your hash function, and you just hash to the product of these two. That's going to of course, make the collision probability smaller, because now you have to hit both times to have a collision. So it might look something like this. Maybe the distance here is slightly bigger, or at least the relative distance is bigger, but we can also repeat this more times. Maybe if we do 3 times, we get this one. If we do it 4 times, we get this one, and so on. But this also shows another problem that we had before, that now all of the probabilities are just getting really small. So even here at distance r, the probability now is, it's tending towards 0 the more times we do this. Here we use one other trick, which is to do independent repetitions of the whole data structure. Instead of just doing the one partition we had before, we're going to do multiple ones. So maybe each of those here have been repeated twice, so they look like this. If we do that, then the probability of having collisions would go up. The probability, because we just need a collision in one of the data structures. And by doing that, we end up with a nice S-type curve like this. So this is really ideal, because now the collision probability at R is nearly 1, whereas the collision probability at CR is nearly 0. Let me show you how we analyze this locality-sensitive hashing, which is going to motivate the changes to this framework I'm going to propose in this talk. Inside our program, our regions are represented as these arrays, and we have multiple ones now, we said. Each of these have a number r to the k. K is the number of times we amplified the hash function. And we're going to do some number of L repetitions. And in each of these repetitions, the points will land in some different buckets here. And the query as well is going to land in one bucket for each repetition. Remember, there was a particular nearest neighbor that we were interested in finding. So maybe it's over here. Here's where it lands in the first repetition. Maybe in the second repetition it lands here. And it's also going to land different places all the way down. We want to know how many repetitions that we should make to make sure that the near neighbor is going to land in the same region as the query. But we're also interested in bounding the amount of collisions we get. So basically, for each repetition, we have to look at all the points that land inside our region. So here is only 1, but here there are 3. The amount of work that we have to do is the sum of all the collisions. So that's going to be L times N times P2 to the K. L, because we need to look at each of the repetitions, even if we have no collisions in there. And then for each repetition, we're going to see N times P2 to the K of the bad points. Remember, we have these 2 circles. This one of R and CR. And these points out here, they're the ones that we're not interested in. And these are the ones that collide with our query with probability P2. See here, because they're further out than CR. We don't pay for the points that are in here, because obviously if we find a point that's inside of distance R, we just stop. So then in the worst case, we can assume that we don't find that. But we can also stop whenever we find something that's within distance CR, because that was the approximation that we allowed ourselves. So that's why in expectation, the amount of work we're going to do is L plus L times N times P2 to the K. If we want to balance out these 2 terms, we can set them equal to each other, which implies that P2 to the minus K should equal to N. We're going to use this equation in a moment. We also have the other problem, like say there's nothing, no blue points in here, there's just a green point, right? Then we only give an acceptable answer if at some point the red point will be together with the green point. So here it worked out, but the probability that it's going to happen in general in one particular repetition, it's probability P1 to the K. And the probability that it's not going to happen is 1 minus p1 to the k. And then the probability that it's not going to happen in either of the repetitions is then that to the L. Okay, so we want this error probability here to not be too big. And we can bound it using a standard inequality as e to the p1 to the k times L. So basically we want p1 kl to be equal to 1. It's a reasonable choice. It turns out to be pretty optimal. So now we can solve these equations. So from this one up here, we see we should choose k to be log n over log to the 1 over p2. If we then insert that here, move p1 to the other side, we're going to end up with L equal to n to the log 1 over p1 divided by log over p2. And remember that we put these two terms equal, so this value here is actually the expected work that our algorithm is going to take for each query. And of course, we have this is also the number of repetitions we've made. So given there are n points in total, the space we're going to use is n times L, which we also write as n to the 1 plus rho, where rho is this constant log 1 over p1, log 1 over p2. Good. So this is the idealized version of locality-sensitive hashing. One main issue here that we didn't talk about was setting k. So we said you should just set it equal to log n divided by log 1 over p2. Of course, k has to be an integer. Remember when we drew the graph of the probability curves? We could choose these different lower curves here. They came from setting k equals to 2, k equals to 3, and so on. But there's no curve that corresponds to this line here or this here. So what we might choose to do is to simply round up here. So we just say, okay, we'll pick k to be the first integer bigger than this value. If we do that, then we don't get this L value here. So let's see what happens if we analyze this right. We still have these two equations that said p2 to the minus k should be equal to n, and p1 to the minus k should be equal to L. And from this one, we got that k should be equal to log n over log 1 over p2. But we now rounded it up, so it's not really implied, but this is how we chose to pick it. Then we end up with L equals to p1 to the minus log n log 1 over p2. This is less or equal to p1 minus log n log 1 over p2 plus 1. This first term here we already knew from before. That was just equal to n to the rho. But now we have this extra p1 to the minus 1. And that's in the title of this talk. And the main problem of this paper has been to try and get rid of this term here. And you might think this is just some analytical problem. Like this just came from bounding this ceiling by this plus 1. If you think about it, you'll notice that this is going to happen in practice always, right? You're never going to be able to set k to this very precise value you want. You could easily have cases where this is tight, maybe log n or log 1 over p2. Say it's like 3 plus epsilon. Then the ceiling is going to be 4, so you basically increased k by 1 compared to what you wanted. So you might say, oh, we just round down instead. But then what happens when you round down is you now have too few regions. And you might end up with just being completely overloaded inside one of your buckets. Say you're in the case where this log n divided by log 1 over p2 is like half. Now when you round it down, you don't apply locality-sensitive hashing at all. So you can't expect to do better than just doing like a brute force scan of the whole database. Before we look into how to actually get rid of this factor, I'm going to show you how big it can be. Because you might look at this, it's just a constant, it's going to make very little difference in practice. Like say P1 is a half, then obviously you don't really care too much about this one compared to this term here, where if n is like billions and maybe rho is a half. But I did some experiments. In particular, I took these data sets from a big survey article about nearest neighbor search on the Jaccard Similarity, which is a measure of similarity between sets. And I computed all the pairwise similarities. I then plotted these on a log scale, normalized by the size of the data sets. We can also think of these graphs as the expected distances or similarities for our query. So if our query wants to find just some point in the top 10%, then P1 will be around n to the minus 1/6. And you see, that means that in this case here, if we said rho was a half, then if P1 is n to the minus 1/6, then we end up with n to the half plus 1/6, which can be a pretty big difference for many practical applications. And there is so much work done into reducing this constant here that it makes a lot of sense to try and reduce this one here as well. You could even imagine many cases where this rho is pretty big enough that once you add this contribution from P1 to the minus 1, you actually end up spending time bigger than n, which is of course a terrible thing, since then you might as well have just done a brute force search of the whole database. Another interesting thing about this data set here, you might expect the small data sets to be further down here to the left, because if they have a similarity between 2 points of 0.01, then it's going to look much more dramatic when plotted in terms of n. Whereas if the very big data sets have a similarity of 0.01, then because their n is so much bigger, they're going to end up further here over to the right. But that's not actually what happened. So when I did this plot, I got that some of the biggest data sets like LiveJournal, Spotify, and Orchid all have smaller similarities. Intuitively, this might simply be because there are so many points now in this space that if they're not all to end up in one big ball, they have to use more of the space. But this again shows how important it is to take into account this factor. So let's talk about how we can reduce this. The idea we're going to use is perhaps the most natural one to consider. If our problem is that we were rounding up the number of buckets to use, and we also couldn't round down, then what about a little bit of each? We're going to have some repetitions with a lot of buckets. We're going to have k rounded up amplifications. And then after a while, we're going to change, and we are only going to do k rounded down repetitions. At this point, we still don't know how many repetitions we need. So we just call this one here B and these ones here A. But other than that, we run the algorithm the same way as before. If we analyze this, the amount of work we'll do is still going to be A plus A times N times P2 to the minus K rounded down from this part of the data structure, then plus B times N times P2 to the K rounded up. There should not be a minus here. We're going to use the notation here that K is equal to, or K rounded up is equal to K plus alpha. So alpha is whatever separates K from being an integer. And that also means that K rounded down will be K plus alpha minus 1. If we look at this part here in particular, we can say A times N times P2 to the K rounded down, that this K plus alpha minus 1 plus B times N times P2 to the K plus alpha. And now, since we know from the definition before, remember p2 to the k is equal to 1 over n. So this is going to cancel, and we're going to have a p2 to the alpha minus 1 plus b p2 to the alpha. And if we use the same optimization idea as before, we would like this here, which is the amount of work that we encounter from looking at collisions, to be equal to this here, which is just the number of repetitions we have. 1 minus p1 to the k rounded up to the b. So that's the failure probability. The probability that we don't see the near neighbor in any of these first b repetitions. We can then multiply this with the failure probability for the other a repetitions, since they're independent. This total error probability is going to be k rounded down like this. And now we employ the same analysis strategy as before. We bound this by e to the minus p1 to the k plus alpha b plus p1 to the k plus alpha minus 1 a. And so if we use the definition of k, so look, remember this is not the k rounded up and down, this is the exact k, then this is equal to e to the minus. And so from this we can infer the following equation. We would really like to have p1 alpha b plus p1 alpha minus 1a to be equal to n to the minus rho. No, this is wrong. So we now have these two equations, the one that we need to have enough success probability and the one that bounds the amount of work that we do. We also have two unknowns, a and b. Remember that p1, p2 were given, n is given, alpha is given from our formula for k. So we can solve this simple system, and then after doing a certain amount of math, we end up with a bound that says a plus b is less than n to the rho divided by p1 1 minus rho. So this is quite nice. We see that we've managed to remove a factor p1 to the minus rho. This is actually tight. We can imagine a certain curve here that has alpha on one axis and then on the other axis the performance of the algorithm. So obviously when alpha is 0, then we don't actually lose anything. We can get this here straight. But then as alpha grows, it increases, and then at some point it decreases again. What we show is that it never gets worse than losing this factor here. So we don't actually have to lose the full factor p1. So to see the significance of this p1 to the rho, I have made this this graph here, which tells you, given a certain value for p2 and a certain value for p1, how much is the saving you have, this p1 to the rho. And we had the example from Netflix earlier. Maybe you had p1 around n to the third. And then if you have your p2, say you want a pretty precise approximation, maybe you will have p2 around n to the minus 0.4. So then we end up in this third spectrum here. So you actually save n to a quarter of each single query that you do to your data structure. All because you did this split in what I call the high probability buckets and the low probability buckets. So in conclusion, we didn't quite manage to remove the entire p1 to the minus 1, but we did show a very simple to implement scheme that removed a big part of p1. It's very interesting to consider more advanced schemes and if it's possible to completely get rid of this value p1. Thank you.